In this video, we will look at an alternative way to define natural transformation. Why will we want to do that? Well, first of all, by giving alternative point of view, we can get a better understanding of what we're talking about. And second of all, the multiplicity of the point of view allow, when we want to generalize or add some extra feature, to choose whichever representation is the best suited for the goal. So if we start from where we were before, we had two categories C and D, two functors F and G, and we were giving ourselves, as part of natural transformation, a family of morphisms in D, alpha x, alpha y, etc., for any F morphism in C, the corresponding square in D would commute. That is, if we go from above or from below, we have a common value which we can denote alpha f. Now this hints at some definition of a natural transformation as a functor between the category C and some category arrow of D. So if we want to make precise this intuition, we can try to define the category arrow D more precisely. So we could give as objects the arrows of D, and so in between two such objects we could define the arrows to be a pair of arrows. Now we really want this to be self-contained, and here if the going from above or from below was a different morphism in D, we would be puzzled. We'll have to carry along that information. So we say, as part of the definition of being an arrow is a pair of arrows between the domain and the codomains of the objects, and such that the above morphism, the above composition from D to E to G is equal to the composition from below, from D to F to G. And to define a category, we also have to define the identity. In this case, the identity is very trivial. We just consider the pair of identity, 1D, 1E in that case, and that would obviously satisfy the condition for being an arrow. And we have to define the composition, and composition between two pair of arrow between X and Y and Y and Z would obviously be the pair of composite arrow, which would give us an arrow of D between X and Z. And since each square commutes, the composition would indeed commute, and that would qualify to be an arrow in D. So we have this composition. Identity is obviously a left and right identity. The way we've defined the composition is obviously associative, because the category D, the morphisms are, the composition for D is indeed associative, and we've defined the composition in arrow D in terms of the composition of D, of the extremities. So arrow D is indeed a category. Now that we've defined this category arrow D, can we try to define this alpha tilde? That is, given some natural transformation, can we define alpha tilde as drawn in cat? So for this, to each object of C, we will associate the morphism of D, which is an object of arrow D, alpha C. And to F, we would associate the pair F of F and G of F. And you can see that by the condition of alpha being a natural transformation, this would be indeed a commuting square, so that would qualify. The pair FF GF would qualify for being an arrow in arrow of D. And obviously when we continue, when we extend that with G, we would have also a commuting square. And when we compose G and F, we would get indeed the composition in D. That means we would compose the extremities and we would get back the alpha tilde of G compose F. And likewise for the identity would be mapped to F identity, which is identity of F, and to a G of identity, which is identity of G. So both properties hold because F and G individually are functorial, and this joint functoriality allows us to verify that alpha tilde, which we have defined, is indeed a functor from C to the new category ROD that we've defined. So we are happy we've defined this functor. Now, what about the other way around? That is, can we define from a functor from C to ROD some natural transformation? Well, remind that a natural transformation is a family of morphisms of D indexed by the object of C. We already have such a family handy. We just apply alpha tilde at each object of C. It would give us an object of ROD, so an arrow of D. And we have to verify now the naturality condition, which says for any morphism F in C, the corresponding square has to be commutative. So the alpha tilde gives us for any F an arrow in arrow of D. That is a pair of arrow of D mapping the domain and the codomains of the initial object of arrow D, alpha C, to the codomain of the arrow in arrow D, alpha D. And we are naming this pair, we're giving them names. We're giving alpha tilde F0 to the first component and alpha tilde F1 to the second component. Now, if we define the functors F to be this alpha tilde followed by domain, and if we define G to be alpha tilde followed by codomain, which are both domain and codomain are functor, they map each arrow to the domain and each arrow of arrow to the first component, etc. Then we have defined a natural transformation. Why? Because remember, the only condition for this to be a natural transformation would be that this square commutes. But the fact that alpha tilde is a functor says that for each morphism of C, we'll have a morphism in arrow D, and part of the definition of being a morphism in arrow D is that the square will commute. So alpha is a legitimate natural transformation. So let's sum this up in a big diagram in CAT, where we can draw everything we've been discussing. So we end up with this diagram where alpha is defined by alpha tilde, or alpha tilde is defined by alpha, and we have the sides which are commuting, that is alpha tilde then followed by codomain will be the same as G, and alpha tilde followed by domain will be the same as F. Now this is basically this reformulation, and so we see a natural transformation as just a functor into a narrow category. But the added value here, in a way, is that we have a good understanding of what a functor is. It's just really a drawing, and we've reduced this complex notion of a natural transformation into just a drawing, and we've done so by constructing this category ROD, which packs a lot of power, and we've been able to abstract the some of the essential mechanic of a natural transformation into this category, and it's a very common phenomenon which appears, and you can meditate on the natural transformation as a drawing into this arrow category, and you can also meditate in this mechanism of packing more power into a category, and we can check some other time that the notion of natural isomorphism that I was discussing previously and I was saying it's not just an isomorphism, it's just actually a whole family of isomorphisms, etc. And we can construct a category which is powerful enough in a way, and in which this notion of natural isomorphism is just an isomorphism. So we would get back, a more natural intuition about this. And this is a general phenomenon. Anyway, so that's another way of defining a natural transformation, one among many others.